Hi. Last week we started to discuss about the basics of the main memory, memory management. This week we are going to continue with the main memory, and then we are going to move on virtual memory and mass storage. Actually, last week we discussed the concept of paging, how we can create pages, how we can fit pages into frames, etc. So let's continue with the implementation of page table. First of all, we had to say that page table is kept in main memory. So page table has a base register called as PTBR, actually page table base register. So that register points to the page table and page table length register. Indicates that the size of the page table. So basically we have two registers. One of them is pointing the base register, and the second, actually the base, and the second one is the points us the length of the page table. So caching page table requires changing only this one register to reducing context switch time. So we know the base, so if you want to change, you need to just change the register. Although storing the page table in main memory can yield faster context switches, it may also result in slower memory access times. So suppose that we want to access location I, we must first index into the page table using the value in the PTBR offset by the page number for I. This task requires one memory access. It provides us with the frame number, which is combined with the page offset to produce the actual addresses. We can then access the desired place in memory. With this scheme, two memory accesses are needed to access data. The standard solution to this problem is to use a special, small, fast lookup hardware cache called as transition look aside buffer, TLB for short. The TLB is associated to high-speed memory. Each entry in the TLB consists of two parts, a key or a tag and a value. So we have a key and a value. When the associative memory is presented with an item, the item is compared with all keys simultaneously. If the item is found, the corresponding value field is returned. The search is fast in TLB. So a TLB lookup in modern hardware is part of the instruction pipeline, essentially adding no performance penalty. Here you can see the paging hardware with TLB. So the TLB is used with page tables in this way. The TLB contains only a few of the page table entries. So here we have a TLB. It's not containing all page table entries. It's just have a small size of containing some of that page table entries. When a logical address is generated by the CPU, the MMU first checks if its page number is presented in the TLB or not. If the page number is found, its frame number is immediately available and is used to access memory. As we just mentioned, these steps are executed as part of the instruction pipeline within the CPU, adding no performance penalty compared. So you can assume that it's very similar to reaching a register. If the page number is not in the TLB, address transition proceeds these steps, where memory reference to the page table must be made. When the frame number is obtained, we can use it to access memory. In addition, we add the page number and frame number to the TLB so that they will be found quickly on the next reference. If the TLB is already full of entries, an existing entry must be selected for replacement. Replacement policies in here can be ranged from least recently used to round robin to random, so based on your choice. So actually, we can consider the TLB in paging Actually, it's a hardware part, but we can consider it as very similar to caching in memory based on data. So we are creating a cache of page table using TLB. So if the entry is in TLB, we can create a fast communication. If it's not, we are going to check the page table to access the physical memory. And also we are going to write that information to TLB to use in next accesses. Okay, so let's move on. Memory protection. Memory protection in a page environment is accomplished by protection bits associated with each frame. Normally, these bits kept in the page table. One additional bit is generally attached to each entry in the page table, called as a valid-invalid bit. When this bit is set to valid, the associated page is in the process's logical address space and thus it's a legal or valid page. When the bit is set to invalid, the page is not in the process's logical address space. So that means it's an illegal move. Illegal addresses are trapped by use of the valid-invalid bit. The operating system sets this bit for each page to allow or disallow access to the page. Here we have an example. So suppose, for example, that in a system with a 14-bit address space, we have 14-bit as our address space from 0 to here. We have a program that should use only addresses 0 to that part, 10468. So given a page size of 2 kilobytes, we have the station shown in this figure. Addresses in page 0, 1, 2, 3, 4, and 5 are mapped normally through the page table. Here we have pages, so based on the page tables, we have frames here for page 0, 1, 2, 3, 4, and 5. Any attempts to generate an address in page 6 or 7 will find that the valid-invalid bit is set to invalid and the computer will trap the operating system invalid page reference. Okay, so we have pages, we map that page to frame table, page table actually based on the frames. And if that page is valid, the valid-invalid bit will be set. If it's invalid, so if we don't have any page on that frame, the bit will be unsetted to invalid. So based on that, we can check if this is a legal move or illegal move. If it's valid, if it's legal, we can give the access to memory. If it's an illegal move, that means this address, this frame is not in the that process's address space, so we cannot give access to memory based on that definition. Advantage of paging is the possibility of sharing common code, a consideration that is particularly important in an environment with multiple processes. If the code is reentrant code, it can be shared. Reentrant code is, let's say, non-self-modifying code. It's never changed during execution. Thus, 2 or more processes can execute the same code at the same time because it's not going to change anyway. Each process has its own copy of registers and data stores to hold the data for the process's execution. The data for 2 different processes will, of course, be different. Only one copy of the standard C library need be kept in physical memory, and the page table for each user processes maps onto the same physical copy of that C library. Here we have an example. We have libc, a C library, so it's shared among different processes. So let's say we have process 1, process 2, and process 3, all of them using that shared library. So on their page table, we can map that, okay, this page will be here. Let's say the first page of C library will be on the third frame. So it's on third frame, it's on third frame, it's on third frame. We have entries on each page table, but all of them pointing the same frame because we are just keeping just a single copy of that shared library. So this is how we can share pages between different processes, among different processes. Memory structures for paging can get huge using straightforward methods. So in this section, we try to explore some of the most common techniques for structuring the page table, including hierarchical paging, hashed page tables, and inverted page tables. Clearly, we would not want to allocate the page table contiguously in main memory. One simple solution to this problem is to divide the page table into smaller pieces. We can accomplish this division in several different ways. One way is to use two-level paging algorithm in which the page table itself is also paged as shown in this figure. So based on that, we can create a hierarchy based on our different page tables instead of just storing all the information, all the mapping on just a page table. We can create an outer page table and a real page table based on that hierarchical manner. We can reach the physical memory. For example, consider again the system with the 32-bit logical address space and a page size of 4K. A logical address is divided into a page number consisting of 20 bits and a page offset consisting of 12 bits. So because we page the page table, the page number is further divided into a 10-bit page number and a 10-bit page offset. So instead of just using a single level, we have P1 and P2. We created our logical address like that. We page the page table, so the page number is divided into a 10-bit page number and a 10-bit page offset. So the logical address will be like that, where P1 is an index to the outer page table and P2 is the displacement within the page of the inner page table. Here is the address transition scheme for that. The address transition method for this architecture can be described as in this figure because address transition works from the outer page table to invert. This scheme is also known as a forward mapped page table. So instead of just one page number and one offset, we divided our page number to two. So we have P1, P2, and D. So using P1, we are going to get the outer page table, and based on the value on the outer page table, we are going to move on to the inner page table, and we are going to use P2 as an offset here, and then based on that value, we are going to move on the physical address, and D will be the offset in here. So just instead of page number and offset, we have two page numbers. We're using this page number as an offset in the inner page table. For a system with 64-bit logical address space, a two-level paging scheme is no longer proper. To illustrate this point, let's suppose that the page size in such a system is 4 KB. So actually it's 2 out of 12. In this case, the page table consists of up to 2 up to 52 entries. If we use a two-level paging scheme, then the inner page table can conveniently be 1 page long or contain 2 up to 10 4-byte entries. If we use a two-level scheme, so we get a huge number of entries too. So instead of that, actually, if you use two-level, the address will look like that. On the other page, we have 42 bits as an inner page number. We have 10 bits, and as offset, we have 12 bits. So the obvious way to avoid such a large table, because these will create a large table, to avoid that large table, we can divide the outer page table, this one, into smaller pieces. Here, suppose that the outer page table here is made up of a standard size page 2 up to 10. So instead of just an outer page, we can create a second outer page. So you can see from here, we can divide the outer page. So based on that, instead of just creating a two-level paging scheme, we can create a three-level paging scheme. Another approach for handling address spaces larger than 32 bits is to use hashed page tables. So instead of creating a three-level paging system, we can use hashed page tables with the hash value being the virtual page number. We can use the hash value as a virtual page number, and based on that we can create hashed page tables. Each entry in the hash table contains a linked list of elements that hash to the same location to handle the collision actually. Each element consists of three fields: the virtual page number, the value of the mapped page frame, and a pointer to the next element. So based on that we can create a hash table like that. Actually, the algorithm works like that. The virtual page number in the virtual address is hashed into the hash table. Here we have an hash table. The virtual page number, here the logical page number P, is compared with field 1 in the first element in the linked list. Here we are going to check that. If there is a match, the corresponding page frame, field 2, is used to form the desired physical address. If there is no match, the subsequent entries in the linked list are searched for a matching virtual page number. So this is how we can create hashed page tables instead of creating a hierarchy between inner and outer page tables. Usually, each process has an associated page table. The page table has one entry for each page that the process is using. One of the drawbacks of this method is that each page table may consist of millions of entries. These tables may consume large amounts of physical memory just to keep track of how other physical memory is being used. To solve this problem, we can use an inverted page table. An inverted page table has one entry for each real page or frame of the physical memory. Each entry consists of the virtual address of the page stored in the real memory location with information about the process that's on the page. So only one page table is in the system, and it has only one entry for each page of physical memory. So for that reason, it's called that as inverted page table. Instead of creating page tables for each process, we can create a complete page table based on the frames. So this figure shows the operation of an inverted page table. Inverted page tables often require that an address space identifier. That identifier must be stored here. That identifier must be stored in each entry of page table, since the table usually contains several different address spaces mapping physical memory. So we have to decide, we have to understand which entry belongs to which process. So storing the address space identifier ensures that a logical page for a particular process is mapped to the corresponding physical page frame. Process instructions and the data they operate on must be in memory to be executed. We already know that. However, a process or a portion of a process can be swept temporarily out of memory to a backing storage, secondary storage, and then brought back into memory for a continued execution. Actually, it's called as swapping. Swapping makes it possible for the total physical address space of all processes to exceed the real physical memory of the system, thus increasing the degree of multiprogramming in a system. Standard swapping involves moving an entire process between main memory and a backing store. The backing store is commonly could be a fast secondary storage. It must be large enough to accommodate whatever parts of the process need to be stored and retrieved, and it must provide direct access to these memory images. When a process or part of process is swapped to the backing store, the data structures associated with the process must be written to the backing store. For a multi-threaded process, all per-thread data structures must be swapped as well. The operating system must also maintain metadata for processes that have been swapped out, so they can be stored when they are swapped back into memory. Here is the schematic of standard swapping of two processes using a disk as a backing store. We have different processes on our main memory. We can swap out a process to backing store, and also we can swap in a process to the memory from backing store and continue the execution of that process. Standard swapping was used in traditional Unix systems, but it's generally no longer used in contemporary operating systems because the amount of time required to move entire processes between memory and the backing store is not proper. Instead of that, we can swap in or swap out, just paste. Instead of moving or swapping out the entire process or swapping in the entire process, we can use the swapping scheme with paging. Most systems, including Linux and Windows, now use a variation of swapping in which page of a process, rather than an entire process, can be swapped. In fact, the term swapping nowadays generally refers to standard swapping, and paging refers to swapping with paging. So when we say paging, actually that term includes the swapping. When we call that swapping, it generally refers to standard swapping. When we said paging, paging refers to swapping with paging. A page out operation moves a page from memory to the backing store, and the reverse process is known as page in. So instead of using the term swap out and swap in, here we are using page out and page in because we are just moving one page of that process. So swapping with paging is illustrated here, where a subset of pages for process A and B paged out and paged in respectively. So let's assume that we don't need this page B, C, and E. We can page out them to backing store, and also we can page in some page of that another process into main memory. And that's it for this chapter. We are going to continue with the virtual memory, but before that, let's take a break. I'll be here in 5 minutes, and we're going to continue to discuss the basics of virtual memory.